Hello, everyone, and welcome to the FusionEPtalks, a student-led webinar on fusion science and technology. My name is Dhaval, and I'm delighted to present our speaker, Riccardo Niccolo Iorio, who will be talking about his ongoing PhD research. Since childhood, they have always been interested in puzzles, and when the moment came to choose what they would want to do in future, Riccardo realized that to enjoy what they have always enjoyed in regards to studying physics, they wanted to continue their way in theoretical physics. And after graduating, Riccardo decided that he has a long-standing dream of opening a chiringuito on the beach, but before going to realize that, he thought that it will be a nice cushion to get some extra qualification. And what better than a PhD in plasma physics and fusion. So here is Riccardo pursuing his PhD in the Aalto University in Finland, and he will be talking about his efforts on solving the confinement problem in the turbulence field with a new approach or a semi-new approach. And without taking more time, I will hand over the stage to Riccardo. Welcome all and enjoy the talk.
Okay, thank you a lot, Dhaval. I will take application for the chiringuito afterwards if you want to join with this wonderful experience. So, as you said, I am Gaia. I'm an Italian. I graduated in theoretical physics in Milan, and then I decided to switch to plasma physics, which I didn't know possibly nothing. And today I'm going to share what I've been working for the last year, essentially. So today I'm going to introduce to you the concept of the collisional brackets. How many of you know about this topic or heard about this topic? Nobody answers, so nobody got it. Okay, so this is going to be a first. So let's start. Well, we all know that fusion physics seems to be a very viable solution for the future, not just from an economic point of view, but specifically also from an energetic point of view. However, although it is very futuristic in a way, it bears a lot of challenges in solving how to confine the plasma itself. And this is related to why? Because the model we try to study are very complicated. Even, let's take, for example, the current model or the usual model that we use in plasma physics. That could be like the Vlasov-Maxwell-Landau system. The presence of the collisions term in this system of equation is the one that actually bears all the difficulties when we try to solve it. So when we want to try to solve this physical equation, we either do it in two ways. We do approximations, since it's very difficult to solve them analytically. And this is also something that we see when we try to solve stuff in electromagnetic, in the electromagnetic fields, or electromagnetism, sorry, where we see that, for example, it's difficult to have an analytic solution out of it. The same principle also applies when we're trying to do plasma physics. But the main reason that the things get even more worse is the fact that when we try to consider collisions, which are actually the ones that drive the plasma or the motion of the plasma inside the plasma itself, or in the tokamaks, which are the great machines that we're trying to build to understand it better, we rely on approximation that either lead to two kinds of models. The one that rely on fluid models, or the one that rely on kinetic models. However, one can also say, okay, perfect. I know that this term is the one that messes up everything. How can I, let's say, study the same system, but in a more simpler way? This is achieved in a very simple way. It's done by either neglecting or approximating even more this collisional term. What is the drawback of this? The drawback of this is that it doesn't allow to understand very complicated phenomena that also take place in fluids, which are essentially turbulent fluids. When we say, for example, or when we study we introduce ourselves to the concept of instabilities. So to try to avoid these difficulties, in recent years, it's been developed reduction techniques that rely on the Lie transformation perturbation theory. This theory is not novel. It has been, it bears the name of his creator, Lie, Sophus Lie. And it was used in the first place, it was used to study the motion of the moon, for example, and to get rid also the fast motions. So plasma physics is essentially the best testing ground for this kind of technique. But what is the problem with this kind of technique? It has two main drawbacks. The first one, since it is a perturbation technique, it gives rise to truncation problems. So like every perturbation technique, when we want to, what we do is we want to arrive at a certain degree of precision, well, then we truncate the perturbation and that's it. And we retain what we got. The problem is that when we do this, we need to be sure, or we need to ensure that the laws of thermodynamics are not broken. So we have entropy dissipation. And this is extremely difficult to do with the Lie transform perturbation theory. It's not impossible, but extremely difficult. Another problem is that when we try to address instead models or collision in a more general framework, when we use a background magnetic field which is non-uniform, then it's not that everything breaks down, but it becomes almost impossible. So in recent years, it's been the growing belief, well, not the growing belief, but many people have been trying to find a different way to approach the same problem, to study the same problem, but without all the hassles that come from the Lie transform perturbation theory. And this has begun in the last 5-10 years, has reached to nowadays to the notion of what is called a collisional bracket. But what is a collisional bracket? It's not just a fancy word. Now, I'm going to introduce to you the collisional bracket in a very simple way. And pardon me if I don't explain it that well, but if you have questions, we can then redo it again, and I will explain it in a very easy way. So, as we all know, the collisional part comes from the Boltzmann collisional integral, and this integral can be approximated by making the assumption of Coulomb collisions to what is called the Landau operator, which is the first expression that we see over here. The difference, although it might seem pretty scary at first sight, which it is in a sense, the thing is that if it can be seen, is actually a matrix, is a multiplication, or sorry, how do you say? No, not a multiplication, but is a contraction of a matrix with a vector, where a vector with a vector gamma, sorry, with a vector gamma is defined by this expression. The projection matrix, though, the matrix Q that is inside this expression is a very peculiar matrix. Why? Is symmetric matrix, first of all, but the most important property that it has is that it's a projector. So it projects is a projector on a subspace which is orthogonal to the velocity difference of the particle we are considering. This will serve us, this property will be fundamental and will serve us very, very well in the ongoing presentation, as it will be clear afterwards. Now, from this general prescription of the Landau operator for collision under the assumption of Coulomb collisions, what kind of advantage can we take out of it? How can we, say, create a new mathematical tool that will serve us well in the future studies of the same problem? The idea essentially follow these lines. We want to create a tool that needs to serve us well and respect certain constraints in order to avoid the problems that we face when we use the Lie transform perturbation theory. So what kind of constraints do we require for this new mathematical tool? First of all, it needs to compute invariants of the system. The invariants of the systems that we all know are the one that technically are the one that we seek for, because they make our life easier when we make calculation or when we program or we do programming. It allows us to better understand and also reduce the complexity of the problem to a lesser degree. The second one is that we want this object to be as general as possible. So it needs to work in functional spaces. In plasma physics, everything is modulated by distribution functions. So the most easy idea that one can have is like, perfect, it needs to work on functional spaces. So this is the reason also behind it. The third one is that it needs to guarantee the entropy dissipation. Why we require this? We require this because we don't want to have the same problems that we have with the previous reduction schemes. From all these requirements, with a little bit of algebra, one can construct what is called the collisional bracket through this expression. Now, if we take a look at this expression a little bit slowly, what does it represent? We have a vector, a matrix, and a vector. So essentially, we are talking about a quadratic form. It's a quadratic form at the end of the day. A little bit more fancy than the one that we are used to, but is the idea and the principle essentially is the same. And the matrix that defines the quadratic form as this specific expression, where here again, the Q is our projection matrix inside of it. Now, the next thing that I want to discuss is why is so novel, or why should I care about this metric? About the collisional bracket, because it's the natural generalization of what we have experienced when studying classical mechanics in the master's or undergraduate courses. Why? Because when we try to address, for example, many of the phenomena that we see or that we study, not just in plasma, but in, for example, in fluid dynamics, quantum QED, QCD as well, we end up with finding systems where there are dissipation, where there is dissipation. So there are dissipative systems. But from what we know, from what we learned in previous experiences, we've just been able to understand just the part that doesn't rely on that. Why? Because the dissipative stuff is extremely difficult to handle. In 1981, two people had the idea, Kaufman and Morrison, had the idea to extend or generalize this concept to the thing that the evolution of any kind of generic quantity that we can think of can be partitioned between as the sum of two different brackets: a Poisson bracket, the one that we are used to, and the collisional bracket. And everything is modulated by what is called the free energy function, which essentially is the difference between the Hamiltonian and the entropy of the system itself. In fact, let's say we suppose that we don't want to deal with the dissipative system, then the entropy, we are not going to consider it. The collisional bracket won't be there, and we will recover essentially the usual evolutional equation that is modulated by the Poisson bracket and the Hamiltonian of the system itself. Now, what is the difference between these two brackets? As we know, the Poisson bracket is an antisymmetric bracket, and essentially it governs the contribution to the dynamics of the system through the Hamiltonian, through the presence of the Hamiltonian. On the contrast, the Metriplectic bracket or collision bracket, the same object, different names, is defined in a very specific way. It's symmetric, but at the same time, it's semi-definite negative. Why? Because we want to ensure that the H theorem, or in other words, energy dissipation, is true, is guaranteed. And this last part, so the collisional bracket, is the one that governs all the or takes into account all the dissipative contributions. So through this little, let's say, equation over here, we are able to separate two effects, dissipative and non-dissipative. Now, as any bracket, like the Poisson bracket, we're very interested in finding what are the invariants of this bracket. But we need to be very careful to know, and also we need to be very careful in knowing that an invariant for one bracket is not necessarily an invariant also for the other one. An example is, for example, the entropy functional for the system itself is not, in that case, we have that is not an invariant for the Metriplectic bracket, while it is for the Poisson bracket. Now, what kind of functionals? Then we might think, okay, we have this tool. Now we need to understand what the simplest functional we can think of, might guarantee, or from which we can find conservation property, conservation laws, which are essentially invariants of the bracket itself. These essentially are the most simplest ones that we can find, which are the mass, momentum, and energy. Now, why are these invariants of the bracket? Simple. Because if we compute this gamma vector that was defined previously, pardon me if I go back, that was defined through this expression. And if you see in this expression over here, and also in the definition of the bracket itself, is a quadratic form, remember that, we find that they are all account to 0 for the mass and the momentum, while for the energy is not exactly the same. Why is that? Because if we compute this vector for the energy, then we will find the velocity difference, the relative velocity, essentially. But when it's but since this matrix W is proportional to a projector matrix, which projects on a subspace orthogonal to the one found by the relative difference velocity, then its contraction with this vector is 0. So since all these quantities are 0, we have that these three are free invariants, since the bracket is null. Now, from this, we have a tool that is generalizing collisions, has invariants. The next thing to check is what kind of equilibrium states that it has. Does it bring Maxwellians in an equilibrium state in the most simple case, or something more fancy? This can be checked in a very simple way. If we employ, since there are many invariants to the system itself, the energy state is degenerate. And since it is degenerate, we can use what is called the energy Casimir principle to find an equilibrium condition, which is expressed by this expression itself. This condition, once we compute the functional derivatives of the three functions that we had before, reduces to this expression itself, which we can call it as the equilibrium condition for the distribution functions. But as can be easily checked already without even integrating or doing anything fancy, is essentially a Maxwellians. So what we have is like we have achieved to rewrite the contribution of collisions in a plasma through a bracket that ensures that entropy dissipation is guaranteed, has invariance, and give the Maxwellians equilibrium states for the simplest model that we can think of. So everything is pointing in the right direction. What is also very important about this formulation is important because the evolution, or the collisional evolution, I would say, is because of, we're talking about functional spaces, what we are considering, we are also considering infinite dimensional spaces, not just through the Hamiltonian formulation, but also when we try to understand, like when we study models that are without dissipation. So this new tool is like we were trying to start with studying on different levels. This tool, or this bracket, has managed to bring this on the same framework, on the same level, these two way of thinking. And this will help us a lot in the next slides. So now that we have this new tool, the next thing to do is, perfect, I want to check if this tool works well in testing case. So the first testing case that one can think of is, okay, I'll go with the guiding center Vlasov-Maxwell model. It's not the most difficult one that we can think of, but we want to see if it works, if it's true, or if what we found is just something fancy or just a new way of rewriting stuff that doesn't bring any kind of new information or else. So for the guidance center and the Vlasov-Maxwell model, what we do is, like, we want to make also our life easier. So see, if we want to make our life easier, we make 3 essential assumptions for the specific model that we're going to study. The first one is that the distribution functions that we are considering will not depend on the gyro angle. The second one is that we assume that there are these 2 unit vectors, one parallel to the magnetic field and one orthogonal to it, by which we can decompose the velocity of the particle itself. This is usually done in the guiding center case, so it's not novel. And as last, we connect the unit vector k with the gyro the leading order of the gyro radius through this relation. Why we take rho 0? Because this is an approximation itself. If we had to consider the full gyro radius, things would get much more complicated. But we just want to check if the things that we done bring something. Okay. Starting from the model that we're going to study is the one that was being studied by Brizard and Tronchi in 2016. So the model consists of these 5 equations, the usual one regarding the Vlasov one, classic one, and also from the electromagnetic contribution to it, paired with the equation of motions and the definition of the current density, the charge density, and the magnetization, 1, 2, and 3. Now, apart from the full equation over there of the model itself that are important to a certain degree, what we are interested now is to find, since we have this model, can we find invariants, or better, can we have a bracket, the same collisional bracket, to this, that can be transported to this new model, or can be used in this new model? What we know from the work of Brizard and Tronchi is that there are two global invariants for this specific model. The one that is given by the total energy, and one is given by the momental function, which are here expressed. Now, as I said before, the collisional bracket will have the same form technically. This is what we think. We have a bracket, okay, so we say to ourselves, perfect, it will have the same form, but can I just, for example, do a transformation of coordinates and this will give me the correct result? The answer is no. Why? Because if I do so, I will end up in having truncation problems again. So I will have truncation problems, and as I said before, I will have to mess up a lot to have the to guarantee entropy dissipation again. And this is not what I want, because otherwise I will just use the Lie transform perturbation theory again. So what we do is we try to take a secondary route to get on the same at the same spot. What we do? Okay, perfect. So we say We cannot do change of variables, but we can do change of variables of a vector. Perfect. So what we do is we analyze, we compute in this new, in the guidance center variables, this vector gamma. And this is the expression that we end up with. Where, as always, rho 0 is the lowest order of the gyro radius, as I said before, but which is an approximation of a steel theorem. Now, cis gamma is defined in this way. Just a second. Okay. Cis gamma is defined in this way. The next thing that we can do is perfect. We're going to compute now this gamma vector relative to the momentum functional and the energy functional. And these two expressions are the one that we get up with. Note that the expression for the energy essentially is nothing else, again, of the relative velocity of the two particles in different of the particle in a different position in just the new coordinates. So things look good at the moment. Now, if we want to have an invariant, as in the previous case, well, what needs to happen is that the gamma vector for the momentum is equal to 0, while the one for the energy, when paired with the matrix W, needs to be 0. The only way that we can achieve this is that we need to select W, the W matrix, in such a way that these two identities are satisfied. And why this expression? Pretty simple. The delta that we have over here is necessary to guarantee that the first identity, this one, regarding the momentum, is satisfied. In fact, if we use it into the integration of the collisional bracket, since everything is integrated, it will yield 0. So this is exactly what we wanted. Regarding the other ones then, is how can we get this? Simple. Since we are contracting since we are contracting this gamma vector with the W matrix, the W matrix is proportional to this projection matrix again, which is defined in terms of the relative velocity expressed through the gamma vector again. So essentially, we're doing the same thing that I presented before to you, but in a different framework. So the choice of this W allows us to have a bracket in the guidance center coordinates and has all the requirements that we need. In fact, this guarantees that the collisional evolution that we have of all the functions, not just the one that we are selecting, it can be like the energy, the momentum, it could be also other ones, they're all modulated by the collisional bracket itself and the entropy. So referring again, we have still entropy dissipation, still guaranteed. So we have, again, works on functional spaces, check. Works, yields invariance, check. Energy dissipation, check. What can we do next? We do the same stuff that we did in the previous slides. We can check what kind of equilibrium distribution do we have. Does it change? Does it get more messy? Is it still a Maxwellian? Very likely it's not going to be a Maxwellian, and this is exactly the case. It's not going to be a Maxwellian. In fact, if we use, again, the energy Casimir principle, we do some calculation, and we end up with this condition. This condition essentially is nothing else that says that the distribution function we are trying to see, to which the system goes, essentially, it's just an exponentiation of the kinetic energy that we have, plus a little drift in the direction of the magnetic field. So not exactly a Maxwellian, close enough, but not exactly Maxwellian. Because of the assumption that we made, it is possible, specifically of the assumption of non-dependence of the functionals and of the distribution functions on the gyro angle, we can try to find analytic solutions in terms of gyro averages. How does it work this one? Essentially, what we do is we express or we expand the velocity difference that we had through the computation of the gamma vector that we saw before in terms of the unit vectors b and k. But making note that this k is different from the other one since we are considering different angles. Now, the gyro averages that we want to compute and that they come out when we try to expand this projection matrix that looks pretty scary, and in fact it is, essentially of this nature. I have avoided to put you the full computation for the simple reason that I like people to have a mental life apart from physics, which is not what we want. So what we do is we cut out the stuff, all this kind of thing. And what we do is we define a parameter, as we always do, and we try to re-express all these kind of gyro averages in terms of these integrals. Somebody maybe has already recognized the kind of integrals. The kind of integrals are just elliptic function, specifically the first and the second complete elliptic function. Now that we did this, what can we do? Perfect. So we check that the collisional bracket is a viable option. It works in a testing round, like the guiding center case. Now, what we wanted from the beginning was perfect. Can we apply this same notion or this new tool, mathematical tool, to more difficult ones? What can we do is, okay, we can start to analyze what is called the gyrokinetic Vlasov-Maxwell model. We're just considering a little bit more difficult one, but not even so different from the previous ones. As we all know, this model, the electrostatic one, is given by this system of equation. Now, if we want to generalize or we want to use this new notion, we also need to upgrade the bracket or the notion of the bracket itself on a more general footing. This can be done by using what is called the guiding center Poisson bracket. So this wonderful and fancy expression. What we do is essentially we follow the same step that I introduced you before. So we define what is called the gyrocenter relative velocity vector through difference of the two Poisson brackets. From this, we construct what is called the projection matrix again. So we still have the same projection matrix, but it's constructed in a much more formal way through what is called the Poisson bracket, the guiding center Poisson bracket that we saw before. From this, what we can do is like the collision part or the collision itself can be enveloped or expressed in a very how do you say, in a very compact way through this expression, which was found by Burby and Brizard in 2015. So you see that what we are addressing today is pretty recent. It's not so old in a way. Given all the, let's say, all the definitions that we got here that relate to a specific vector and the flux, collisional flux vector, but these are just definitions that we're not interested in completely. These are just to give a reason to what is written on the slide itself. Everything can be reassembled to give essentially what we wanted from the beginning. So the gyrokinetic collisional bracket or Metriplectic bracket again, which is this expression, which is essentially, this is the same that we found for the guiding center case and we found previously to the guiding center case that we derived from the Landau operator. Now, why is so I still want to stress out why is important the way it's written. One might think that, yes, but I mean, fancy way of writing it, but what does it tell me? The importance of how it's written is, as I said previously, is that this is a quadratic form, and it allows to compute and immediately spot invariance of the system in a very easy way. So the mathematical structure that was kind of hidden in the mud through the Lie perturbation theory now is more apparent, is more simpler to understand. And as I said before, everything is also concentrated or concentrated or goes around what is around the projection matrix. This is what is the central, the MVP, if you want to call it, the MVP of these brackets. And in this case, in this general case, what we are interested now is still the energy conservation, but also now we have the toroidal angular momentum. Now, for the energy conservation, we can always guarantee that this is going to be energy conservation. Why? Because by the way the bracket was constructed, we know that this is the identity that needs to be satisfied for energy conservation. But if we always choose one of the function A or B to be the energy, this is what is going to happen because of the construction that it has. In fact, this is what is going to get to zero. So energy is not a problem. The main problem comes from the toroidal angular momentum. Why is that? The problem comes when we try to analyze two different variants of the same model. One where we don't have magnetic field, and one where the magnetic field is not absent, so is present. If this can be better understood from, if we start by looking at the energy and momentum functional for the gyrokinetic case in this way. So from this article, or one year ago, we have that the momentum and Hamiltonian gyrokinetic functional have this very bizarre form, not very friendly one, with the macroscopic fields defined by these expressions. Okay, the fact that we have a derivative with respect to electromagnetic fields of the kinetic energy is what is going to break essentially everything. In fact, if we compute the functional derivative of the toroidal angular momentum, so this lovely guy, we end up with this expression. Now, in the case where there is no magnetic field, the second term is completely absent. And what we have is that we can find, and we can demonstrate that there is toroidal angular momentum conservation. So it's an invariant. Why we can do this? For one simple reason. There exists, in the case where there is no magnetic field, a functional relations that relates the electrostatic potential to the space of distribution. In fact, what we have is that the phase space itself reduces from a 2 degree of freedom to 1. So reduces just to the space of distributions. In the case instead where we have the magnetic field, this property, if we want to call it, doesn't exist anymore. Actually, the phase space itself earns 2 degrees of freedom. So we don't have no more than 1-to-1 correspondence that we had in the case where the magnetic field was absent. So what we have at the moment is a bracket that conserves energy, but doesn't conserve toroidal angular momentum in the case where we have magnetic field. How we can address this? Is there a way we can try to think maybe to rewrite what we did? What we can do is, perfect, we start from what we know. What we know is that the identities that govern the invariants of the system for the bracket, for the collisional bracket, are given by this first guy and the second guy. This one is the energy, as we all know, and this one is for the momentum. Now, as you can see, this gamma is not the usual gamma that we are used to in the gyrokinetic case, because we know that it doesn't work. So what we can do is we can try to generalize this new gamma by adding extra stuff. And these extra terms are essentially linear operators in the electromagnetic fields, E and B. Why we use E and B? Because we also want that the theory itself needs to be gauge invariant. This has happened, like we speak of relativity, QAD. Everything needs to work in any case. So if we use this new definition of the gamma, because of these identities that needs to be satisfied, this will lead to two constraints, which are the following ones. These two constraints are the ones that we need to compute who these linear operators LE and LB are, because in principle, we don't know who they are. We need to compute them. We sure know that it will depend on functional derivatives of the energy and the momentum, but we don't know which phase they have. Now, some might argue that this is not the best idea. This is true. It's not the only idea that we can come up with. It's not necessary in principle that the first condition, for example, needs to be there. One can say that we don't need this contraction. We just need to say that these two operators, when evaluated with respect to the energy of the system, they yield zero. This is another way of looking at it, but I believe this is much less general in a way, but this still needs study and research behind it. What we can, to close everything, also because I think I've lost you or your time, is that, can we say that this is a good generalization? Yes, for one simple reason. Because first of all, if we put B equal to 0, then this part is unnecessary. And we recover exactly the gamma of the electrostatic case with no magnetic field. So it's a good indicator that what we are doing is in the right direction. Second thing that I want to stress out again is that this condition, why we just have this condition, not the previous one, the extra term that comes out of it, because we know already that this extra term is 0. Why? Simply by definition, again, because energy from that specific part, with the specific part, this one, is 0 when contracted with the gamma omega. I'll just stress another thing and then I'll stop. The omega itself, oh, sorry, not the omega, sorry, the W itself is the one that now is playing the same role that was playing the guiding sensor case, where we had to select what kind of W was needed to ensure invariance. So very likely, also in this more general case, if we assume this condition again, then we will have like an extra condition that the W will have to fulfill. And this might maybe lead the way for X to solving the problem, but it's still unknown. So what we can conclude from this long discussion. I hope that I've been able to introduce to you a little bit to the concept of the collisional brackets and to the fact that the most important part out of it is that it doesn't break the first and second rule of thermodynamics. It allows to compute invariance of the system we want to study in a very easy way. And secondly, it can be applied almost everywhere. Second thing that we learned is that we gain and we have good results from the guidance center case. So we have proven, until future disproved might be or come out, this is a viable solution to get rid of all the hassles that come from the Lie transform perturbation theory and all the truncation problems related to it. And last but not least is that we've shown that we can be further generalized also to include more complex models, but at the same time we end up with wrong answers or not the answers that we actually looking for. So what we have is like an incomplete theory of the bracket itself. Is a very good mathematical tool, but it's still incomplete. It needs to be refined better. And if we can manage to also break this or break through this wall that we have in front of us regarding the gyrokinetics, electrostatic gyrokinetics with the magnetic field different from zero, we might also be able in the future, this is just my opinion obviously, to come out with a theory or a reduction scheme where every model is covered by or can be analyzed by it. And this will be very, very useful, not just from a theoretical point of view, but also from a numerical point of view, because most of the problems that we have also from a numerical point of view is that when we're trying to do numerical models, they don't last that long. This is why the introduction of a bracket like this from a numerical point of view will be pretty useful, because one, it will also allow to have longer simulations. At the same time, it can also upgrade, and I'm not an expert in numerical simulation, but I think that there is still no electromagnetic codes related to it, but maybe I'm wrong. But this is the end of my discussion. I hope that you enjoyed it, but that's it. Thank you very much to all.
Yes, thank you for the talk. I have a relatively general question. So you mentioned that you briefly mentioned numerical implementations. Are you aware of whether any work in that direction has been done? Of course, of the theoretical framework that you mentioned here, either in plasma physics or in other areas of, let's say, statistical mechanics?
Statistical mechanics, no, unfortunately, no. I can try to ask to a friend if you like, maybe. But no, I don't work in statistical mechanics, so I don't know that much about it. I can talk for plasma physics at the moment. The group that I work with, which is essentially divided into, there is a section which is for theoretical studies, a little bit, which is the one I'm in, and the other one which is more numerical simulation orientated. And the main problem now is that the codes that they have is just rely on the electrostatic case. So this is not the implementation of the full electromagnetic case with
right,
with non-uniformities of the magnetic field background. So the theory behind this talk might help in that direction, also because the current simulation, I'm not an expert in it, and they're not bad, but they last very for a short period of time. And what we want to achieve in tokamak is when we put something in, then it keeps staying there for a good amount of time so you can extract energy. But the simulation that we run, they run very, very slow times. So this might, I always use might be of help for the future. Might be also help in statistical mechanics. Why not? Could be, yes.
And I guess, yeah, sorry.
I just finished. Actually, because this kind of concept is true that is not related essentially to the, how do you say, to plasma physics itself. Because as I said before, the concept of the collisional bracket comes out actually from studying the dynamics of fluids.
Sure, yeah.
So also plasma physics can also be tackled through statistical mechanics methods. So if there is I've always been a huge supporter of, you can try to merge stuff. Why not? Absolutely.
So I guess that also means we're still far away from any experimental validation.
At the moment, yes. We're not super far away, but we are far away because we're still trying to figure out how to solve this problem of the conservation of the momentum. Once that is done, then a numerical scheme can be coded, and then a simulation can be run to see if exactly what we did is correct or not.
Okay, thank you.
You're welcome.
Riccardo, can you go to the slide number 8 on your presentation?
Just a second. Yeah.
Okay, so here you say it's a projector on the subspace orthogonal to V minus V bar.
Yeah.
So what does this V and the V bar actually mean? Yeah.
V minus V bar is the relative difference velocity. So what you do is you analyze, since when you analyze a plasma, you have what you say, particles are going everywhere. Mm-hmm. So you cannot concentrate, it's not that you take a statistical approach, but you cannot concentrate on every particle. So when you say, okay, perfect, I'll try to understand how the particle, or what is the particle in two different positions. So this is what it's saying to you. V minus bar is the relative velocity that the velocity has in two different, not two different positions. So just say something. No, it's two different positions. Sorry, my bad. Two different positions. Is the difference of velocity that the particle has in two different positions.
So it's basically like acceleration, that because if particle is in two different positions, it's also changing the time. So it's like how the particle is accelerated over.
Well, you need to understand that what happens is, imagine that, okay, imagine that you got the guiding center, okay? The guiding center, imagine that this is the line of the magnetic field is going there. So the particle, what it's doing is like, yes, gyromotion.
Yeah.
It's doing like this, but also at the same time, because of the presence of the electromagnetic fields, what it's doing like, is not just rotating, but it's also drifting.
Yes.
So drifting right, left, up, down. Nobody knows what it does. So what you can do is, like, there is no point in following the velocity of the particle itself. It's much more useful to see how the relative velocity of the particle itself goes. So this is what you use. But at the same time, is something that, let me check if I wrote it. No, I didn't wrote it. I can send you some notes that I wrote. I think I wrote somewhere that explain better why you concentrate on this velocity difference compared to just the velocity of others, so you can have a better understanding of it.
Okay.